Alright, so in this video here we're going to be looking at something called the energy equation. Normally this video should be broken up into two segments, but just so that we can get through the equation itself and how to apply it, it's going to be a bit longer here. So if you're this far, you've probably already gotten to know what the Bernoulli equation is, and we're just going to write it here real quickly just for your reference. It's the pressure at point 1 plus rho g h1 plus rho v1 squared divided by 2, and that's all at point 1, and that relates to what's going on at point 2, the pressure at point 2 plus, whoops, that should be plus rho g h2 plus rho v2 squared, that's velocity at point 2, divided by 2. So there's a couple things about the Bernoulli equation here is that none of these terms account for things such as losses. And these losses can be due to things such as friction. It can also be due to shaft work. So for example, if you have a pump or something attached to it, you might be delivering energy to the system, or you could be taking energy out of the system if you have a turbine. And by that I mean, suppose you have a pump here and you have a fan blades here, and it's going to be delivering energy, and so you have shaft attached here, and it's getting power from some electrical source, and it's rotating, and it's delivering power to some sort of fluid here. Of course, it can go the other way as well. You can have some fluid, and then you can have a turbine here, and as the fluid passes through the fans of or the blades of a turbine in here, it's going to be turning some shaft, which of course can be producing power as a result of being connected to a generator. So the Bernoulli equation doesn't count for that. So we're going to look at what's called the energy equation, which does account for those sorts of things. So first of all, if we were to divide the entire thing by rho g, let's just see what would happen. Let's just divide by rho g here. If we divide by rho g here, those guys cancel out. If we divide this term by rho g, we get rho out of the way there, and we're going to get a g on the bottom. And then the same thing is going to happen on the other side as well. So we just divided the whole thing, whoops, let me get rid of that, by rho g. Now if you look at every single unit here, we call this, it's in terms of head, and every single unit has units of distance, or of, in this case it can be of meters. So if you were to work out all these units, you would get meters out of it. Height, of course, is just meters. Velocity squared divided by 2g, you'll get out meters, and so forth. So this is now written in terms of head. Now, we're going to add a couple terms onto here to account for these losses that we described over here, the friction and the shaft work. So let's rewrite this. We're going to have P1 divided by rho g plus H1 plus V1 squared divided by 2g. Now, plus, imagine we have a pump and it's delivering energy into the system. So we're going to have the head of the pump, and we're going to write comma here, useful, the useful head that's delivered to the pump, because of course pumps and turbines and all sorts of things aren't 100% efficient. We'll get to that in a sec. And that's going to be equal to P2 divided by rho g plus H2 plus V2 squared, oops, that should be a 2 there, divided by 2g, and then on this side of the equal sign we're going to have plus the head of the turbine, the useful head of the turbine extracted, so it actually comes out of the turbine, plus any head loss, so that's capital L here, and that is head loss. And that head loss can be due to friction in the pipe and things like that. So if you think of a pipe here, and if you were to blow it up and look at it under a microscope, of course it's going to be bumpy. And as the liquid or fluid passes through here, or the gas passes through, of course due to that friction it's going to slow it down. So it's not a perfect system. So as a result you're going to get some losses there. Alright, so this is our new energy equation that we have here. Now sometimes you're going to see one other thing, and it's called the kinetic energy correction factor, and that comes in front of these terms where you have velocity here. And that this alpha here we say is the kinetic energy correction factor. And usually this is close to or equal to 1. And in a question you'll always be given it. It's not something that you're typically asked to derive. And what it is that the kinetic energy of a fluid isn't always exactly equal to just v squared over 2g. So we have this correction factor to account for that. Okay, so now we're just going to get a clean screen here, and we're going to just start all over here again. Now let's look at this these other terms that we added to the energy equation. We have the pump head and the useful pump head. So that is the energy, or the head in this case, that is actually being delivered to the fluid. So when you think of a pump, of course, it can make a fluid go uphill and things like that. So it's clearly delivering energy to the system. However, of course, pumps aren't 100% efficient. Nothing is. You get losses as a result of friction and heat and things like that. We have something that's called eta. It's the Greek letter eta, which is the efficiency factor. And so we always have something that is defining how efficient the pump actually is. So the efficiency of a pump is going to be equal to the power. So we're going to have here a W with a dot on top to denote power. So the power of the pump, the useful power of the pump, so that's what that U is for down there, divided by the actual power of the pump. So what's coming out versus what's going in. Okay, so this is what got delivered to this fluid, and this is the power input. And that makes sense, right? Of course, it's always going to be less than 100%. Wouldn't it be great if it was over? But we know that if you get eta greater than 100%, you know you went wrong there. And so anyway, therefore, we have the head of the pump. The head of the useful head of the pump is going to be equal to the power of the pump, the useful power of the pump, divided by the mass flow rate multiplied by G. We're going to define that again here in a sec. And of course, if we substitute in here what the power of the pump is, we can just substitute eta in for that. So we'd have eta of the pump times the power of the pump divided by the mass flow rate times G. So you're probably wondering, what is this mass flow rate? So let's just come up here and just define that real quickly. Well, we have, it's simple, m dot, the mass flow rate. So when you have a fluid that's flowing through something, you're going to have the mass of it and how much of that is going per unit time. So in other classes or other places you might have seen this dot here, and that is with respect to time. So it's the time derivative of a variable. So for example, just for your reference, if you have x dot, that's actually just dx by dt. Y dot would be dy by dt. So this mass flow rate, this m dot, and it's just going to have units of kilograms per second here. All right, so quickly, you know that the density of a fluid is equal to the mass divided by the volume, and therefore the mass is simply equal to the density multiplied by the volume. And I'm writing out VOL for volume so that we don't get confused with the V that we use for velocity. And therefore then the mass flow rate can be equal to the volume, or the density times the volume flow rate, because they're just going to be divided out by the unit time. We also know that volume itself is equal to area times a distance, such as meters. And therefore our volume flow rate is going to be equal to area times meters per second. And look at that. that's velocity right there. So let's just come right over here where we've got some blank space and write that down. Our volume flow rate, which is going to be cubic meters per second, is simply equal to the area times velocity. And that makes sense here, right? We've got meters squared there, and velocity is meters per second. And then we get back out our units that we're looking for over there. Okay, so we've got the pump, the head of the pump defined, and now we can do the same thing for the head of the turbine. So we're just going to take that and delete that and get a blank screen. Alright, so the head of the turbine, whoops, here we're just going to go back. There we go. The head of the turbine, we're going to do the same thing here. The useful head of the turbine is the amount of the head removed from the fluid. Removed from fluid. So before you saw that the fan or the pump delivered energy to the fluid. Now we're extracting it, or we're taking it away. All right. So this is equal to the power. So that's W dot. And of course, if you recall work. The time derivative of work, which would be power, so work W dot, which is work dot, is joules per second, and that's power. So the work of the turbine divided by the efficiency of that turbine multiplied by the mass flow rate times G. And that's equal to the work of the turbine, the useful work of the turbine, or we can also say sub E as well for extracted, divided by M dot G. And that's because we have here that the efficiency of a turbine is equal to the power of the turbine divided by the extracted useful power of the turbine, sub E or sub U. Now I'm just going to quickly draw this out so to help you understand what this is looking like. So imagine we have some water here, and now we have some pump connected to it. So this is going to be my pump, and it's going to be going this way. So the flow is going this way. Here's my pump. Okay, and this is the power of the pump itself that's going into it. And then of course what's coming out of it is going to be the useful power of the pump, because of course there's some losses that occur in there. And then that's being delivered to some tank or some reservoir, okay? Some tank of water. And so we have here then the efficiency of the pump is equal to the power of the pump, the useful power of the pump, divided by the power that got delivered to it. So this over here takes power. But now imagine we have some pipe connected. So we're pumping water up. Now we're going to extract energy from it. So in this case with the pump, we delivered energy to the system, and we got the water to go uphill and into a tank. Now the water is going to come down. We're going to take energy out of it. So now imagine we have some big dam here, some big reservoir here, and it's filled with the same water. Then at the very bottom here there's an outlet, and we have some turbine connected to it. Alright, so now the water's going this way, and we've got some blades that the water's going through to push it, and it's going to be delivering power. And then we can have some generator over here. And if you think of it, of course a turbine's turning this shaft here, and up here there would have been a shaft as well that was getting turned and by some electrical motor or some electricity from somewhere. So we have shafts here. Alright, so as the water is coming out of here, here we're going to be delivering power. Alright, so you can kind of see the difference between the two systems here. So it's delivering power. And then the efficiency of the turbine, which is what we have just written up here, is the power that comes out of the turbine. So the extracted power, or the useful power. Oh, sorry, let me just erase that. The power that's coming out that's being delivered to it, divided by the power of the turbine that is coming out of it. So let's just draw where that would be here. So here is the power that's going into the turbine, and here is the extracted power. Oops, that's coming out. Okay, so you can see that the extracted part is always what's coming out, or the useful part, but they're on opposite sides of the fraction line between the turbine and the pump itself. Now, the one other thing that we haven't covered yet here is the head loss. So we have this other term that you saw here, H sub L, and that is considered to be irreversible head loss, and that's going to occur between points 1 and 2. Alright, and that's due to all the components in the system that have some sort of losses as a result of friction or things like that. And you'll either be given that in a question, or it's just something that you look it up on a chart. But for the purpose of this lecture, or this explanation, we're just going to be given it. Okay, so we have the energy equation in terms of head. One thing we can do is multiply every single term by m dot g, the mass flow rate and the gravity constant. And then what this will do, so we're going to multiply the energy equation when it was in terms of head, in terms of its heads, multiply it by m dot g, and that's going to give us terms that are in have power units. So it's going to have power terms, and of course the unit will be watts. Alright, so let's write that out now. So we're going to multiply everything by m dot g. So the first three terms we can just write it as we're going to distribute it outside of the brackets. So we have P1 over rho plus, and then this kinetic energy correction factor, alpha 1 V1 squared divided by 2 plus GH1, and then we still had the power of the pump, and that's equal to, now I'm going to start over here again, what's going on at point 2. So we have the mass flow rate, m dot, multiplied by P2 divided by rho plus alpha 2 V2 squared divided by 2, plus GH2. And the other two terms we had there were the power of the turbine plus, instead of head loss, it's just, we call it now the mechanical loss, the mechanical power loss. Now let's just look at these three terms here. They each have some unique names for it, so that you know what they are. This is what we call the flow energy. Now you know from your study of kinematics and kinetics that this is kinetic energy. Kinetic energy. And then this term here is going to be potential energy. Energy. Alright, there we go. Now it looks like we've run out of time to do the question, so that'll be done in a separate video, and really this should have been broken into two segments as well, but at least you've got what the energy equation is, and then to apply it actually is quite simple. It's just as easy as applying the Bernoulli equation. You have to sometimes make some assumptions and make sure you know what's going on for each of these terms here, and it's quite straightforward. So join us in the next video to go through a question where we actually get to apply the energy equation. Alright, thank you.